right, well, we're going to talk today about the fundamental theorem of calculus, which sounds really important, and it is. It is really important. All right, so we're going to look at the second fundamental theorem, which we did last time, also the first fundamental theorem this time. Okay, so let me remind you what the second fundamental theorem of calculus is all about. In this unit, we're discussing the definite integral, which is a limit of sums of products of function values times these finite widths delta x. And as the number of rectangles gets arbitrarily large, or as the width of each rectangle gets arbitrarily small, these things go together, then this limit will exist no matter what choices of c's we take. That is for certain good functions like continuous functions or only finitely many jump discontinuities. Okay. And we learned that a better way to compute definite integrals than taking a limit of Riemann sums is to look for antiderivatives, because it's a remarkable theorem that the integral from a to b of f of x dx is the difference between that antiderivative at b and at a. Okay, and this had all kinds of implications, because if you integrate velocity, then you get the net distance traveled. If you integrate marginal cost, then you get total cost. If you integrate density, then you get the total mass. Anything that's got a density or a velocity to it, you can integrate it to get the total amount. Oh, thanks for the pop-up ad there. Got some spyware infected on this computer, I guess. So we realize now that antiderivatives are a more serious process than something we just did for fun. We have to think about tabulating antiderivatives, and so we rebrand them as indefinite integrals. And then we started collecting them. So there's the power rule in reverse, sines and cosines, the inverse trig functions, they're all there. We don't quite have a program for finding antiderivatives of lots and lots of different functions. That's mostly in Chapter 6. We'll do a little bit of that at the end of Chapter 5. Okay, so that was our review of Wednesday. Did you enjoy it? Good. So I want to look in the other direction now. Let's take a function. For this case, we'll take the function which takes t to t cubed, and we're going to look at a new function, which is the integral from 0 to x of f of t dt. So take the cubing function, pick a point x, and integrate the cubing function from 0 up to x. Let's find that function and its derivative. Okay, well, first let's find the function. I've got a nice little picture of a Riemann sum here. And just to remind you how this went, we divide the interval 0 to x into n pieces. Each piece has width x over n, because the interval is x wide, and there are n divisions. Okay, so you set each marked point to be the index I times the width delta t. And then you form a Riemann sum, which takes each delta x times each f of something in between xi and xi minus 1. And in this case, I'll take the right-hand endpoints. We get a bunch of x's and a bunch of n's. They all factor out. And what's left out is the sum of the cubes of all the whole numbers between 1 and n. Okay, we can look that up. We have a formula for that. It's x to the fourth divided by n to the fourth times 1/2 n plus 1, whole thing squared. So once you simplify all that, what you get is that the right-hand Riemann sums with n divisions gives you x to the fourth times n squared times n plus 1 quantity squared divided by 4n to the fourth. And as n goes to infinity, the numerator here is a polynomial of degree 4 in n, just like the denominator. So all you have to do is look at the coefficients of the n to the fourth term in the numerator and the n to the fourth term in the denominator. Their quotient is the limit, and in this case it's x to the fourth over 4. So another way to write this integral is just x to the fourth over 4. Okay, and the second question was, what is the derivative? Well, now that we have the equation for the function with just x's in it, we can take its derivative like we normally would, and we get x cubed. Okay, and if you go back to the beginning, you see we started with the cubing function, and we ended with the cubing function. Right, find the integral, find the derivative, and we come back again to the cubing function. Now, this is something we can do in general. Take any function which has an integral, so it is integrable, that is, maybe it's continuous, or at most finitely many discontinuities, and we can define a new function, g of x, to be the integral from a to x of f of t dt. Now, in case you're wondering that we're suddenly doing something new with this t is just the name of a variable. X is the name of a variable too. Most of the time, I like x to be the name of my inputs to functions. Okay, and if I'm going to let x be the name of this variable and this variable, I can't also make it the name of this variable here. You can't use the same variable for two different things. So I have to call this something else. I'll call it t. Whether I call it s or theta or 6, whatever, this integral is going to be the same. That's just a variable that says integrate this function. Okay? We call that a dummy variable because it doesn't appear in the name of the function. It's just there to integrate over. All right, so you want to think about having a function and moving the right-hand endpoint of the region that you're integrating over, okay? And thinking about the area of that region as you slide around that right-hand endpoint. And the question is, is there anything about f, the function that you're integrating, that will tell you something about g, this area function? Here's an example. This is my function f. It goes up, down, wiggles around a little bit. And I'm going to create the area function of that function f. Okay? I'm going to try and graph g of x and the area under the curve of f between 0 and x simultaneously. Okay. So between 0 and 2, the function is positive. And so I get a little bit of positive area right here around here. And you can see now this green function is the graph of the g of x area function. Between 0 and 1, I see I got a little bit of positive area. Between 1 and 2, will g be positive or will it become negative? G will still be positive. Will it be more than it was before? Will it be more g than there was before? Yeah, because I'm adding on a little bit of area. And in fact, the amount I'm adding on is much more than the area I had before. And so g increases at an increasing rate. Now, between 2 and 4, I am continuing to accumulate area. But the amount of area I'm accumulating per distance in the x direction is not as much. So g will continue to increase, but not as much, not as fast of an increase. Okay? Between 3 and 4, g will still increase, right? But again, not as fast as it was increasing before because I'm adding less area. And that continues all the way up to this point here. I have now added all of the area under this region of the graph above the x-axis. After this point, the area that I'm adding, or the area that I'm accumulating, is now negative. Right? I'm subtracting area from this point onward. So what's going to happen to g? It's going to start decreasing because I'm taking away area. Okay? And as I move a little bit further, I'm taking away more and more area. So the rate at which this function decreases will increase. When I get to this point here, I'm still subtracting area, but not as much as I was over here. So I decrease a little bit less, and decrease a little bit less. And between 8 and 10, I am decreasing at a constant rate that looks something like that. So there's my function g. Okay. It's a little bit hard to work through, but if you picture the graph, and you picture all these pieces of area that you're accumulating, you can put together the graph of g. Okay, now let me compare g and f and all the things that we were just saying on one chart. On the interval 0 to 2, we notice that the function f is positive, and we use that to say that the function g was increasing. We also said that the function f was increasing, and so the rate at which g is increasing is itself increasing. That means g is concave up. The graph of g is concave up. Between 2 and 4.5, the function is still positive. The function f is still positive. And so the function g was still increasing. But it wasn't as positive as it was before, so the function was decreasing. And g is taking on less area, and so the rate at which it's increasing is decreasing. That is, the graph of the function is concave down. The graph of the function g is concave down. Between 4.5 and 6, f becomes negative. So in our accumulation, we are now subtracting from g. G is decreasing. Okay, because f is decreasing, g is going to be concave down. Between 6 and 8, f is negative, so we're still subtracting, which means g is still decreasing. But the amount we're subtracting is not as much as before, so f turns out to be increasing, and the graph of g is concave up, because we're subtracting less area than we were before. And between 8 and 10, f is still negative, making g decreasing, but f doesn't have any increase or decrease to it, so the rate of change of the amount of area we're accumulating in g does not change. So there's no concavity in g. Okay, so we just put in a table everything that we had in the picture, and now let's compare what's happening in these columns of f and these columns of g. Notice that when g is increasing, f is positive, and when g is decreasing, f is negative. When f is increasing, g is concave up, and when f is decreasing, g is concave down. All right, so when g is concave up, f is increasing, and in both cases, f is behaving much like the derivative of g. F is behaving like the derivative of g, meaning that g is looking a lot like an antiderivative of f. Okay? So do you believe me? Okay, well, let's state the theorem for real now. This is called the first fundamental theorem of calculus. It says if you have any integrable function on the interval a to b, define its area function g of x. If there's a point x where the function f is continuous, then the function g is differentiable at that point x, and the derivative of g at that point x is equal to f of x. Okay? So if f is continuous, then g is differentiable, which is even better than continuous, and the derivative of g is f. Okay. So that's great. That sounds pretty fundamental, doesn't it? Because it connects this differentiation and integration. Okay. So, we're going to prove the first fundamental theorem of calculus, just like we proved the second fundamental theorem of calculus last Wednesday. When I was in college, I was president of the math club. No surprise. And we had a math awareness week. We actually finished up math awareness month. Did you guys know that last month, April, was math awareness month? No, see, this is the problem. We need math awareness month, so that we know when math awareness month is. It wasn't April. And so during math awareness week, when I was in college, we had a big quad, and I went out into the quad, and with my chalk, I proved the fundamental theorem of calculus on the sidewalk, so that everyone would walk over the proof of the fundamental theorem of calculus. And this is the proof I gave. The center one. Yeah. Main quad. Yeah, we're big time now. Okay, so this is not actually my proof. This was one of the first proofs written down. We are going to look at the difference quotient for g, because that's how we find derivatives if we don't have any other rule, right? We need to find the limit of the difference quotient. So we're going to take g of x plus h minus g of x over h. And I'm going to assume h is positive. To do it when h is negative, you just do everything in reverse, and then you put them together. Okay, what is g of x plus h? If you look back at the function, it's the integral from a to x plus h. And g of x is the integral from a to x. And if you subtract those two, then you get the integral from x to x plus h. This was that additive property, the integral, in the limits. Okay? And we're going to divide it by h there and there, just like we do. Okay. Now this is supposed to be an integral from x to x plus h. And we proved another property of integrals that allows you to estimate an integral by its maximum value on an interval, and its minimum value on an interval. So let's take the maximum value of the function on the interval x to x plus h, and we'll call that capital M sub h. And we'll take the minimum value of the function on the interval x to x plus h, and we'll call that number little m sub h. Okay, and because we have the comparison properties of the integral, this is technically property 8, as it's listed in section 5.2. The integral is less than or equal to the maximum value times the width of the interval, and it's greater than or equal to the minimum value times the width of the interval. This is the one where we took the graph, and we took that region under the graph, and we put it between two rectangles. And the area of the larger rectangle was m, capital M, times h, and the area of the smaller rectangle was little m sub h. Okay, so this was the integral that we wanted to estimate. Notice there's a 1 over h here, so to compare this to this, I need to divide this by h. Luckily, I have an h to spare. So what I get is that m sub h is less than or equal to the integral from x to x plus h of f of t dt. which I could also write as g of x plus h minus g of x over h. And that is all less than or equal to capital M sub h. Okay, so here's the deal. As h goes to 0, capital M sub h goes to f of x. And as h goes to 0, also little m sub h goes to f of x. So if that's true, if this quantity goes to f of x as h goes to 0, and this quantity goes to f of x as h goes to 0, what can you say about the thing in the middle? It has to go to f of x too. Whose theorem is that? Mr. Squeeze's theorem, that's right. So because the squeeze theorem, this thing also has to go to f of x, which is exactly what we wanted. The limit as h goes to 0 of the difference quotient of g is f of x. So the derivative of g is f of x. Okay? Now this point is actually kind of confusing until you draw it. So I have a nice drawing here. Capital M sub h is supposed to be the maximum value on the function on the interval x to x plus h. So I have here the function graphed in nice thick color here. The maximum value is obviously up there. The minimum value is obviously down there. And I'm going to let h get smaller and smaller. So as you see h getting smaller and smaller, the maximum value starts creeping downward. Okay, it starts creeping downwards towards f of x and so on until it looks like in this case it's going to reach f of x. What about that minimum value? Well, all this time the minimum value happens here at the minimum value of the function. But if we continue to decrease h some more, we will pass up that minimum value. And now suddenly m sub h is creeping up towards f of x. Okay? So as h goes to 0, the maximum value is going to decrease down to f of x. And the minimum value is going to increase up to f of x. That's as good as it can get. Okay? And this is really because the function's continuous, which is why we have that important assumption in the fundamental theorem. If we try this on a function which is not continuous, say we've got this function that has a value here and then jumps down here to a different continuous function, look what happens when we plot the capital M sub h and the little m sub h here. Capital M sub h decreases down to here, okay? And little m sub h doesn't move until we pass up this minimum, and then it starts to increase back up again. Whoops, sorry. But the biggest little m sub h is going to get is this, this value right here. It's not going to get all the way up to f of x. It's separated because the function's not continuous. Okay, so this is why we need the continuity assumption in the proof of the fundamental theorem of calculus. Okay? So, great. Okay, so story time. I'll tell you about some of these mathematicians that have studied or proved or thought about the fundamental theorem of calculus. The first of these is James Gregory, a Scottish mathematician from 1638 to 1675. He was an astronomer and a geometer. He thought up the idea of transcendental numbers, and he thought that pi was transcendental. He wasn't able to prove it, but he had some good evidence for it. And he proved a geometrical version of the first fundamental theorem of calculus as a lemma, but he didn't take it any further because he was interested in other stuff. He didn't really understand where this was going to go. It was more useful for him to prove something else. This actually happens a lot in math even today. There's a branch in mathematics called differential geometry, and there's a branch in mathematics called differential topology. And those sound very similar, right? But the geometers are interested in one thing, and the topologists are interested in another thing. A lot of times if you read their papers, they're proving the same things, but the geometers are calling the theorems calling one set of results the theorems, and another set the lemmas, sort of baby theorems. And the topologists have the same facts, but in opposite order. So the geometers' theorems are the topologists' lemmas, and vice versa. They care about different things. And so that's what Gregory was doing. He didn't care so much about the first fundamental theorem. He just wanted to do his little geometry stuff. Okay, moving ahead to Isaac Barrow, English mathematician, professor of Greek, theology, and mathematics. See, back in those days, you could do all these things and still be a learned man in all of them. Nowadays, we are much more specialized. And if you look at their hairs, you can see that they come from this early 17th century generation. Okay. Barrow was able to think a little bit about the fundamental theorem of calculus, but he didn't quite understand it that well. He talked some more about it with his student, Isaac Newton, who we all know. Okay, Newton was a late 16th century professor, at Cambridge in England. In England, in the years 1665 through 1666, there was a massive plague, a bubonic plague, that swept over England, and so the University of Cambridge basically shut down. Everyone went home for like 2 years. And so Newton went back to his farm, and he did some of his best work during that time. He was uninterrupted by, I don't know, students and office hours and things like that. So he just did all kinds of work, and during that time, he invented calculus. But he was actually kind of a shy guy. He didn't do a whole lot of publishing because he didn't like to subject his work to the criticism of others. But eventually, in 1704, he printed a book called Optics, and an appendix to Optics, he wrote this little treatise called Tractus de Quadratura Curvarum, treatise on the quadrature of curves in 1704, in which he laid out his ideas for what he called fluxions and fluents. All right, so that's Newton. And then we move on to Leibniz. So this later generation, much larger hairdos, right? Leibniz as well. Fantastic hair here. Okay, so right around the same time, right? 1643 was the birth of Newton. 1646 was the birth of Leibniz. Leibniz as well was a philosopher and a mathematician. You may have read some of Leibniz's pieces in your philosophy courses. And he was in Paris during the time 1672 to 1676. And this is about the time that he invented calculus. Okay, and he started publishing his work in 1684, and then another paper in 1686. Now, I wasn't able to write the titles of his papers in the slides because they are way too long, but here you go. Okay, so Leibniz's paper in 1684 was called, in English, A New Method for Maxima and Minima as well as Tangents, which is impeded neither by fractional nor irrational quantities, and a remarkable type of calculus for them. That was page 1, I guess, the title. But there we have for the first time the word calculus in print, as it relates to a mathematical discipline. Leibniz invented the word calculus, as well as the words derivative and integral. His paper in 1686 was called On Recondite Geometry and the Analysis of Indivisibles and Infinities. So they sure knew how to name their papers back then. Okay, so analyze these dates here and see if you can see what the controversy, about the controversy that erupted here. So Newton invented his calculus, or his form of calculus, the fluxions and the fluents, 1665. Leibniz, 1672. So who came first? Newton came first, 1665, 1672. Who published first? 1684, 1704. Over 20 years after Leibniz published his claim to the invention of calculus, Newton came along and published his stuff. Now, lots of people knew what Newton had done and hadn't published, but they wanted Newton to get his stuff out there. Because Newton waited so long in getting his calculus out into the field, there erupted this huge debate as to who had really invented calculus. Okay, so Leibniz had his people who would say that Leibniz invented it, and Newton had his people who would say that Newton invented it, and Leibniz had like ghostwriters who would publish anonymous articles saying, by the way, Newton's a dope and he stole all his stuff from Leibniz. And Newton would have the same thing. He'd have his little lackeys write articles criticizing Leibniz and calling him a poser. It was like the 17th century equivalent of an East Coast, West Coast rap war. We had people gunning down other mathematicians on the streets, and it was just really bitter. And Leibniz actually went to his grave disgraced because people thought that he had stolen all these ideas from Newton. But now we know that both of these men share the credit for discovery of the calculus. All right. And there is on the web a website called the Mathematical Genealogy Database. And if you go in there and you click my name and you look for my advisor, who was Shlomo Sternberg, and his advisor, who was Wintner, and his advisor, who was Lichtenstein, and his advisor, who was Kummer, and his advisor, who was Weierstrass, and his advisor, who was Guterman, and his advisor, who was Gauss, and his advisor, who was Pfaff, and go back 13 generations, you'll get not to Leibniz, but to Leibniz's advisor. Okay, so Leibniz and I are in the genealogy first cousins 12 generations removed. There you go. So I guess I have to come down on the Leibniz side of all that. Okay. What'd you say? Yes, yes. My last name is German. I guess that's how it happened. I share many letters with Leibniz as well. Okay, maybe someday I'll appear on one of these slides. I doubt it. I know, first I got to get my huge wig. Okay, so let's put these together. We have the first fundamental theorem and the second fundamental theorem of calculus. The first fundamental theorem says if you take a continuous function and then you integrate it and then find the derivative of that function, you get back the original function. Okay, take the function, find its area function. The derivative of the area function is the original function. Okay? The other function, the other theorem which we learned last time is that if you have a function, you take its derivative and then you measure the definite integral of the derivative, you end up back where you started. Well, at least you take the difference between the function values on the endpoints. So the integral of the derivative of something is an evaluation of the original function, its net change. Okay, so there you have these two seemingly unrelated geometrical constructs, right? The slope of a line tangent to the curve and the area of a curved region. Why should these things be related? It's really the miracle of, you know, one of the fundamental achievements in mathematics, basically in the second millennium, right? 1,000-year summit in mathematics there. Okay. So what does that mean for us? Well, it means that we have a new class of problems we can do. We can find derivatives of functions which are defined themselves in terms of integrals. So let's take a look at this function here. The function h is the integral from 0 to 3x of t cubed dt. This is a function of the variable x. Remember, t is not the variable of the function. It's just the variable that we're integrating over. And whether we had it t or s or whatever, the function would be the same thing. Let's ask ourselves what the derivative of that function h is. Okay. Well, I actually know two ways to do this. The first way to do it is to use the second fundamental theorem of calculus. That is to compute this integral directly. Find the integral from 0, find the antiderivative of t cubed, which is t to the 4th over 4. Plug in t equals 3x. Plug in t equals 0. That one was easy, it's 0. Subtract them, and what you get is 1/4 times 3x to the 4th power. Okay? Multiply that out, and you get 1/4 times 81x to the 4th. And if you differentiate 1/4 81x to the 4th, you get 81x cubed. Does that make sense? Okay? And this we could have done on Wednesday, not anything new from today. Let's look at it now from the first fundamental theorem of calculus perspective. We can think about this function as the composition of two functions, g and k, where g is integrate up to u of that cubic function, t cubed dt, and k of x is 3x. Right? So one of the functions is integrate, and the other function is multiply by 3. And when you have two functions in composition, the derivative of the composition is the product of those derivatives. So h prime of x should be g prime of u times k prime of x, because h is the composition of g with k. Okay, now what is g prime of u? G is just the integral of t cubed. So by the first fundamental theorem, the derivative is t cubed, or whatever cubed. Okay, so g prime at k of x is k of x cubed. G prime of anything is that thing cubed. K prime of x, well, k is just 3x, so k prime of x is 3. So what do I get? I get 3x cubed times 3. 3 cubed is 27, times 3 is 81, and so again, I get 81x cubed. Okay, so do you all agree I got the same thing? Good. All right. Now, there's a lot of variations on this theme. If you have an integral which is defined, if you have a function which is defined as an integral up to a function k of x, and the integrand is f of t dt, then the derivative is f of k of x times k prime of x. Whoop, sorry. Okay, now what if your function is not in the upper limit, but in the lower limit? Then you can take the derivative again, but this time it's a negative sign. So instead of f of h of x, h prime of x, it's the negative of that. Now why should that be? Well, if you think about integrating between two limits, if you increase this limit and the function is positive, you're going to increase the function. Right? You have to picture a graph between my hands here. Increase one limit, you're going to pick up more area, and so the area will increase. On the other hand, if you increase the lower limit, move it here, the amount of area you're picking up is smaller. So increasing the lower limit decreases the area, which is why the derivative here has that negative sign. Increasing the lower limit will decrease the area. Okay, if you have both at the same time, you're integrating between two functions, then you can actually split the difference. Right? One of them is the integral from 0 to k of x and apply the first rule. Right? The other one is the integral from h of x to 0 and apply the second rule. The derivative of the first one is f of k of x times k prime of x. The derivative of the second one is f of h of x times h prime of x, and you subtract them. Okay, this, if you read other math books, this result here is sometimes known as the Leibniz rule for integral, or Leibniz's theorem for integrals. Okay? But it's essentially first fundamental theorem of calculus taken in two different ways. All right, any questions about that? Okay. So then, let's look at another example. We'll do the integral from 0 to sine squared x of 17t squared plus 4t minus 4. So here is the method with the the first fundamental theorem of calculus. A nice way to summarize the first fundamental theorem is that the derivative of the integral is the integrand. Okay? So the derivative of the function which integrates up to sine squared x of all this stuff is all this stuff with the variable substituted for sine squared x. So we have 17 sine squared x squared plus 4 sine squared x minus 4. So each instance of t gets a sine squared x replaced. Now, sine squared x is still a function of x. So in differentiating, chain rule says you have to multiply by the derivative of sine squared x. And when you do that, you get 2 times sine x times cosine x. Okay? If you wanted to do it the second fundamental theorem way, that is the anti-differentiate first method, then what you have to do is anti-differentiate this polynomial. So it becomes 17/3 t cubed plus 2t squared minus 4t. Then you plug in sine squared x. So you get 17 times sine to the 6th power plus 2 times sine to the 4th power minus 4 times sine squared. Then you have to differentiate. When you differentiate the sine to the 6th term, it becomes 6 times sine to the 5th times cosine. You see here we have a sine to the 4th, sine to the 5th, cosine. This term is for 2t squared, so its derivative will be sine cubed x cosine. Here we have sine squared, sine cubed, cosine. Okay, so all the powers of sine and cosine are lining up. Which way would you rather do? In this case, it's probably 6 of one, half a dozen of the other. Which one you would prefer? Okay, let's change it up a little bit, and we'll do this function here, h of x, which is the integral from 3 to sine squared x, 17t squared plus 4t minus 4. Try this one. What'd you get? Isn't it the same? Well, let's take a look. If I'm going to use the first fundamental theorem. Oh, that is a typo. That should be a 3 there, right? Because I changed it to 3. The derivative of the integral is the integrand evaluated at that top limit there. So we get 17, again, sine squared x squared, plus 4 times sine squared x minus 4. Then again, the derivative of the sine squared x. And so I get something which looks exactly like what I got before. Now, is that a typo? Well, no, not exactly. That's a good question, though. Why is the derivative of the function which integrates from 0 to sine squared x equal to the derivative of the function which integrates from 3 to sine squared x? Well, what is the difference between these two functions? One's got a 0, one's got a 3, right? But what if you subtracted the integral from 3 to sine squared x from the integral from 0 to sine squared x? What would you get? You get the integral from 0 to 3, right? The integral from a to c plus the integral from b to c is the integral from a to b. And so subtracting these two integrals gives you the integral from 0 to 3. Now, what is the derivative of the integral from 0 to 3 of all this stuff? Well, that's just a number, and the derivative of a constant number is 0, right? So these two functions, the integral from 0 to sine squared x and the integral from 3 to sine squared x, they are different by a constant, and so, of course, they have the same derivative. Okay, the difference between those two functions is a constant, so their derivatives are the same. Okay, and if you go back to the statement of the first fundamental theorem of calculus, you notice that, actually, I'll scroll back. That's probably too far to show you because I have to go through all those moving pictures. But the statement of the first fundamental theorem of calculus doesn't ever involve anything about the lower limit. The derivative of the function which integrates from a to x is f of x. It doesn't have anything to say about f of a. And so you get the same derivative. Another way to think about it is with the picture, right? Here's a, here's x, and if we change x, we know how the function changes. But if we move a up here and then do the same changes on x, well, the difference, the amount we're adding or subtracting is still the same. We've chopped off a finite, some large amount. But as x changes, the amount that either integral changes is going to be the same. Okay. So that's all done. All right, let's try one of these nasty ones. Okay, so those of you who prefer the second fundamental theorem of calculus are stuck trying to find an antiderivative for sine to the fourth. We haven't really done that yet. The best you can do is use a trig identity to relate sine squared to cosine 2x, and then you'll have a polynomial in cosine 2x. You'll have cosine squared of 2x, which you'll have to use the same trig identity to get in terms of cosine 4x. So you get something times a constant, something times cosine 2x, something times cosine 4x, and then you have to integrate each of those. Okay, and maybe we'll be able to do that on Wednesday. But it's worth exploring whether the first fundamental theorem will get us there faster. And in fact, it does, because the derivative of the integral is the integrand. So we'll plug in sine to the fourth of e to the x. Right? The integrand is sine to the fourth of t. So the derivative will be sine to the fourth of e to the x. Now, e to the x is still a function, so we have to multiply by its derivative, which is e to the x. And we also have change on the lower limit, so we have to subtract the change which comes from there, sine to the fourth of x cubed times 3x squared. Okay, so we got upper and lower limits changing as x changes, and so the integral will increase on one end and decrease on the other as x increases. That make sense? Okay. So this shows that you can't always rely on the anti-differentiation technique if you want to find derivatives of functions defined as integrals. Okay. So is that the only reason why you would ever need to use the first fundamental theorem of calculus? No, actually, some functions are completely impossible to find elementary antiderivatives of. So an elementary function is one that you can basically describe by buttons on your calculator, right? It's got powers and sines and cosines and exponentials and logarithms and fractional powers and roots and all that stuff. And if you take the derivative of an elementary function, you get another elementary function because you know the derivatives of all the elementary functions. But if you try to find an antiderivative of an elementary function, it may not necessarily be another elementary function. It may not correspond to buttons on your calculator. And so you don't have a closed form expression for the antiderivative in which to plug in. And more to the point, there are some functions which we want to study which are defined naturally in terms of other integrals. And so the fact that the derivatives of these integrals is whatever's in the integrand is actually kind of a significant scientific statement. Okay, here's an example of a function which we do not have an antiderivative for. E to the minus whatever squared doesn't have an antiderivative. And it's not that we haven't found it yet. It's that we've proven theorems, theorem of Liouville, that says that there's no elementary function whose derivative is that. Well, maybe we just shouldn't look at functions like that, but this is actually a very significant function here. It measures the bell curve. Okay, e to the minus t squared traces out a bell curve. And so area under this curve, well, this is very relevant to you guys, right? Because anytime something's created on the curve, what's being measured is your position and what percentage of the class you are better than. Okay, so that's a very relevant integral to compute, but we cannot compute it analytically. Okay, but we can find its derivative analytically because the derivative of the integral is the integrand. So erf prime, if erf is this function up here, is 2 over the square root of pi times e to the minus x squared. Why is it called erf? Error function. I don't know why it's called error function. I think when you compound errors, then they distribute away from the average in this normal distribution. Okay? The 2 over the square root of pi, that's kind of interesting. It's the constant which makes the integral from minus infinity to infinity of this function exactly 1. Okay? If you took e to the minus x squared and integrated between negative infinity and infinity, you get the square root of 2 pi, which is a nice fact that you learn when you take complex calculus. Okay, but for our purposes, we can combine the error function with other functions. Say we take the function erf of x squared, and we want to find its derivative. Well, the derivative of erf of x squared is erf prime of x squared times the derivative of x squared. I think I'm the only one who pronounces it erf, by the way. And here's the derivative of erf, 2 over square root of pi, e to the minus whatever squared. In this case, whatever is x squared. And the derivative of x squared is 2x. So we have 4 over the square root of pi, x e to the minus x to the 4th. So say you got some, I don't know, some statistic which changes over time, and you want to find the rate of change of the accumulation of that statistic, or the probability of some random variable lying in an interval where the endpoint of the interval changes. This would be its derivative there. Okay, we cannot compute the integral explicitly, but we can compute the derivative using the first fundamental theorem. Other cases where you have functions which are defined, like they're interesting, but they're also defined in terms of other integrals, the future value of an asset. So you've got some business or some equity, and you want to sell it, right? So you need to figure out how much it's going to be worth over its lifetime. And money in the future is not as useful to you as money now. So money in the future decays exponentially in terms of its current rate to you, right? How much is $1,000 worth to you 5 years from now? It's not worth $1,000 because if you had $1,000, you could do a lot more with it. So the future value is the total sum of all of the revenue generated by this asset, damped by basically inflation from here to eternity, right? From time now, forever and ever and ever. Okay, so that's pi of s is the profitability, and so you can accumulate all the money that it's going to get for you in terms of what it's worth now. And so if you wanted to sell it, this would be a good price for it. Okay, and if you wanted to find the derivative of the future value, it's basically the profitability times the inflation rate, I guess, or the discount rate. Here's another one from economics, the consumer surplus of a good. It's an integral not over time, but over quantity, where f of q is the demand function, the amount that's they'll pay for it, minus the equilibrium price, and this q star is the equilibrium quantity. Okay, what's all that about? I have a nice picture. So you all know about the supply and demand curves. As something gets more expensive, the market will supply more of it, but people will demand less of it. And the intersection of the supply curve and the demand curve is the equilibrium price and quantity. So if this is the supply curve and this is the demand curve, then what happens in equilibrium is that this much is going to get sold and this much is going to get charged for that. So the product of how much is charged for each unit times how much is sold is the market revenue. That's how much money is generated for the people selling it. Now, this part of the demand curve represents people who would have paid more than the current equilibrium price. Okay, it's like, here's a nice example. We just passed Easter, right? And around Easter time, the Cadbury cream egg shows up in the drugstores. And everyone loves Cadbury cream egg. The demand for Cadbury cream egg goes up until Easter, and then it decays pretty rapidly, right? So now if you go to CVS, and if you're lucky to find them, they'll be like 25 cents or 50 cents. And you go in there and you're like, wow, I would have paid $1 for a Cadbury cream egg, and now they're only 50 cents. So you buy one, and you think, I saved 50 cents. Well, no, you didn't. You spent 50 cents. But you spent 50 cents less than you had expected to spend. And so in your head, in terms of utility, you have 50 cents more than you thought you would have. Okay? And that's what's called consumer surplus. It's the amount that you feel like you saved by spending less than you were prepared to spend. The more you buy, the more you save. Not the more you buy, the more you spend. But the more you buy, the less you spend compared to what you were expecting to spend. Okay, so that's consumer surplus. And since it's defined in terms of an area, if you want to write down an equation for it, that equation will have an integral in it. Okay? So this is producer surplus, which I think means what? I used to know this. Producer surplus means that, I guess it's the amount that they should not have gotten because they found people to spend more for it than they wanted. But the firm's goal is to minimize consumer surplus. And so they do that by releasing the Cadbury cream eggs before Easter and charging a lot for them, and charging not so much for them after Easter when the demand goes down. Okay. So price tiering is a way to minimize surplus. Okay. So here we have first fundamental theorem and second fundamental theorem. They link these two marvelous operations in calculus, derivatives and integrals. And we learned about the calculus wars. There's a nice book called The Calculus Wars by Jason Barty. And if you want to check it out, you can read the whole story. And there's a math teacher in Indiana who replayed out the entire drama of the calculus wars on Twitter. So if you Google calculus wars on Twitter, you can see how she recreated it with her whole class. And like Newton and Leibniz are tweeting and arguing against each other. It's pretty cool.